Okay. What is the importance and what is the main outcome we are actually looking for this course? Why we are studying this course? We are studying this course for what? Performance evaluation, which will help us compare between software or compare between hardware platforms or defining bottleneck in the performance. And when we say that, we are looking for the hardware itself, and we can come and say, oh, you know what, this specific memory is causing the issue, which is lowering the performance by this amount. Solution, we have to increase or decrease the speed. Okay. And of course, when I say performance evaluation, we look into what? Execution time, as I mentioned in the last lecture, right? CPI, which is basically the count of the number of cycle per instructions, right? And if you remember last time, we said the average CPI in case there is our classes of the instructions, right? And then also we are looking into the power consumption. And then later on, it might be today or next time, we're talking about what? Amdahl's law, which is defining where is exactly the pieces is actually causing the limitation and constraints in the performance. Why I'm saying this? Because, the project will come out of this. For instance, I will give general ideas and you guys will think about it. And then I will send to every single group a message. Okay, I'm saying, hey guys, I'm gonna write an announcement, group A, those are the couple of topics. Look in one of them, and select, and then you can tell me by next Monday and so on, okay? So one of the projects we can do, all of you guys are really familiar with Raspberry Pi, right? Raspberry Pi. Raspberry Pi is considered something is called single computing node or single computing board, right? It has a computer, but it's limited in terms of resources. And there is a ton of companies using it for building weak laptops or, for computer visions or whatever, right? One of the projects you can do is to bring Raspberry Pi, for instance, 3 or 4, or, the computing node of the Raspberry Pi is something look like the memory, right? And you start running different computer vision algorithms or software like OpenCV or Neurosticks or whatever, right? And then you will start comparing performance, and you will see which software will fit which version of the Raspberry Pi, and you will report it as a project. Again, one of the way for you to look, because this course focus on performance evaluation, right? You will take couple of platforms like Arduino, Raspberry Pi, whatever, and you will run the same software on them, and you will start collect the performance evaluation methods, and then you will start drawing a conclusion out of this to discuss what is happening for this software. It will go in this X platform versus Y platform. Why is the best for this software to be hosted by this platform, and it's not actually great to be hosted by that platform? Does it make sense? Any questions? Any questions so far regarding this part?
So it's just a performance study.
Exactly. Then there is another idea. Let's say you have one platform. Let's say just I bought Raspberry Pi, right? What about if I run different languages or different compiler versions? Like, Python versus C implementation of one of the computer vision, like YOLO or whatever, right? Computer vision algorithms, right? What will be the consequence if I use Python versus C? What actually the consequences of running, for instance, revision of Python versus the other revision of Python. So they're gonna be what? Studying the compiler's effects with performance evaluation. The other thing that which is like yearly I ask students to do, because my background is security, is basically asking them to run crypto primitives. Have you guys heard about crypto?
Who
That's
hasn't?
a very veritable word.
Crypto. So that's my job, my background in crypto. So basically, cryptography. Or you guys could call it, here cryptography, somehow like that. But it's cryptography anyway. So the cryptography, it's a set of algorithms used for encryption and decryptions and used for securing data, which is considered the main component in cybersecurity. So any security protocols are using what? Crypto primitives. And these crypto primitives is what? Mathematician or your mathematical modeling. So you will take this mathematical modeling, you implement it in different platforms, and you start looking into the evaluation of the performance. Examples, like, hash function. Other example, public key algorithm. Other examples, symmetric encryption. Other example, digital signature.
Professor,
Yes.
so far, all three projects are performance evaluations. One on programs running on the Raspberry Pi, one on performance or compiler
I'm
performance.
giving example as Raspberry Pi. I'm not actually limiting you on a Raspberry Pi. I'm just saying.
So program performance, compiler performance, and cryptography algorithm
Evaluation on
performance.
different platforms.
Okay.
Right? Those are many algorithms. Now, I'm actually looking for even difficult stuff, which is not really hard for you. It's gonna be easy. You know what? We can look into new competition sponsored by NIST. Have you guys heard this word, NIST? NIST is a National Institute of Standard and Technology. It's an agency here in the United States. It's called National Institute of Standard Technology. They are responsible for making standards, and they're making the crypto standards. So now there is one competition. It's called LWC, lightweight crypto. Those are targeting what? Small, tiny devices. What is small, tiny devices we can use? Arduino. Have you guys heard about this Raspberry Pico? Have you heard about this?
Yeah.
It's like a $4 or something, maybe you can look into the Rasp W2Z, for instance, maybe Rasp WZ0, ZW0, those tiny tiny devices, basically. I think there is a problem in a national wide for buying a Raspberry Pi. I'm not sure if you guys are following the news or not, but I'm looking for a couple of Raspberry Pi so I can use them in NASA project. And the prices in the internet now is really nuts. It's really bad. Have you guys tried before? It's bad.
The Pi Picos are just on back order everywhere. The only way you can get them is scalpers, and
Exactly.
they charge
And even worse. There is a website I use all the time. It's called New Arc. This one, they told me that I can, I already placed the order, right? They said you will receive it in 2023, something like that. Then there is another thing which I love, which will be great, and I will help you with this. For something is called future edge computing clusters. Future edge computing clusters. Have you guys heard about this? Future edge computing clusters.
Oh, I don't know if I've heard about the future part, but edge computing is always some sort of edge server doing the calculations for a program of something.
What is
And
the difference between edge computing versus high performance computing?
Edge computing versus, I actually don't know.
I will tell you. So there are two different types of computing, right? Something targeting high end, something targeting what low end. What is this? Low end, that means, you know, IoT, which is basically constrained in power, resources on chip, plus software limitation, plus memory limitation. Examples, right? RASP clusters. 1 bit scope blades. 2 turing pi, which is turing pi with Jetson Nano, turing pi with rasp base, and turing pi with Jetson plus rasp. Okay, I'm gonna show you those things on the internet now. Okay, now high end is what we call it HPC community, high performance community. Those are what? Servers, AWS, Azure, Watson. Those are like bunch of what? Servers, right? Super computers, blue waters. The other one is called Oak Ridge super computer. What is those? So those are thousands of computing nodes, have bunch. Yes, they're correct. So it's a bunch of what? Bunch of supercomputing nodes. Each node, it has terabyte of memory, GPUs, and CPU multi-threading with cores. And also in the top of that, it has what? It has FPGA with something is called HBM. HBM is what? High bandwidth memory. Okay, sounds good. So what is the rule of this? What is the rule of this one? For the edge computing, we put it into the context of what? Smart city or Internet of Things. Imagine that I build a rover, right? And I would like to do a localization or a local computing on the rover, right? That will be hosted by the edge computing. But imagine that, you know, the result that I would like to get, it need more computing elements and it need more power, right? I will send it to something called backend, and that will be going in a high performance computing. Then you connect between of them using what? Communication networking protocols, like NVLink. Have you guys heard about NVLink, right? You never heard about it? So, you know, NVIDIA, they built something that's called NVLink, which is like a hyper communication device that can jump in the top of GPUs, which will allow this GPUs to work like a one GPU with really powerful computing elements and also very powerful memory. Imagine whatever I mention in front of you now is not 100% covered by this course, but you need to know it because you know science is moving forward, right? So you need to know what's going on with a little information as a graduate, so you can move forward to work with these companies, right? Now, what I can do, I can show you some of these things, and then, we can move forward to some of the material for today. So, I back here into my main computer, and I can say Turing Pi. This is Turing Pi. Can you look at it?
I don't think we can see what you want us to see.
Oh, you cannot see it? I'm sorry. Can you see it now?
Yeah.
Okay. Can you see Turing Pi? Turing Pi 2 version, as I mentioned, right? One which has multiple racks of the Raspberry Pi computing nodes. Can you see this slots here? Each slot allow you to have a Raspberry Pi computing node, and nearby there is an IO port, so you can take whatever you would like to communicate with, analog or digital devices. Can you see my cursor?
Yeah, we can.
Yes.
Exactly. So this is actually very, very unique. It's a very unique, look at it, very unique platform. And you can actually use it to be a very powerful computer at home, and it will cost you $200.
I mean, assuming you could get the pies to put in it.
I know it should be $30, but now in the black market for almost $100 or $85.
I got a question, Professor.
Yes, please.
This doesn't seem incredibly efficient. I mean, yes, you have all these individual Raspberry Pis, which is great, but each one of them is going to have the overhead of an operating system, even if it's a headless operating system like the small Linux kernels.
True.
What is the advantage of this over having a bigger, more powerful machine that you then containerize out?
Okay. There are two things, right? Everything is relative. There is no 100% answer for a question, except it's 1 + 1 = 2. So for this specific part, believe me, there is a certain application will benefit from this, while the cost is important. So if you remember in the beginning of our discussion about this course, right, we said what cost versus performance, right? So if I have $300, right, and I would like to achieve this performance, right, if I find a good match, I will use it, even though there is a solution that it will be, wow, it give you better performance. Do you agree?
That is true. All right.
So in that case, this is not a bad solution, because end of the day, if you look into larger, even, servers or, supercomputers, right, there is off-loop balancing, because each node by itself is doing its job, right? But then, while they are moving, there is an overhead. But is this overhead tolerated? Is this overhead acceptable when not affected on my budget in terms of performance and money? You know what I mean? Then, you can say yes or no. In general, this can be running, imagine all of this, TensorFlow, Caffe, Kubernetes, Jupyter's, and all of the AI modeling, it will be benefiting from such a kind of architecture in the edge computing context. Then they already have another one, which is called Turing Pi. I'm communicating with those guys for almost 3 months. And we have a discussion about, here, for instance, right? They already put here one Jetson Nano with a couple of Raspberry Pi. So they are making something called heterogeneous edge computing. That means multiple different accelerators coming from different backgrounds. They are working together in one system. And also they are running all of this list of stuff from, TensorFlow to MaxNet, Caffe, and of course, the baby of IBM, Kubernetes, which is the software scheduler that will allow you to use all of these nodes, no matter how many nodes you have, so you will get the best performance. It's called Kubernetes. I would recommend you guys to play with and look at it in details, okay? Now, the other company, which is very good, I mentioned to you, and I have here a server in my office for almost $12,000. It's called bitscope. I was searching for it in the morning. and they built racks of PCB boards that will allow you to communicate multiple nodes of the high-end Raspberry Pi, and they put it into cluster. And this is one blade, and these blades can be infinity number of what Raspberry Pi nodes. And Los Alamos National Lab worked with them closely to build multi-stories building, having millions of Raspberry Pi nodes for experimenting the new of the future supercomputers. So that will be cheaper for the scientists who are building the new supercomputer than spending a couple of $1 million to build the prototype. So once they are done with all of the design and everything perfectly fine, right? They will go ahead and spend a good amount of time for production. So that's why, you know, edge computing, when you scale it up, you can move into the high performance computing. Sounds good? So one of the projects that you can even look into it, you can look into one of these blades. You try to run one of the AI inferences. You can find an internet or crypto or, you know, image processing or video processing, and you can end up actually doing a very good comparison. And the good thing, there is a bunch of software already published in GitHub. You can actually adopt it. You don't need to write software. You just need to figure out how to move the data in the right position in the processor, and you will just collect the performance metrics, right? Some of you guys know that, you know, software has issues when you will move a certain version into a certain platform. You might actually have some issues, right? Software companies fixes this problem, and they built something called Docker. Have you guys heard about it? You guys heard about Dockers?
Yeah, Docker is basically a program that containerizes other programs.
No, it contains the dependencies from the operating system. So, you know, yeah, I mean, let's say that I'm running Python 3 point whatever, right? But my computer, it forgot this library and this library and this library, right? The Docker will take the whole entire dependencies from the operating system that is running correctly and give it to you in a container, and you will be running it even though that's your environment, it doesn't have all of this information, and it still will be operating. Make sense? So why I'm saying that, so it will be easy for you guys to do what? To work with whatever you want to do with without having issues to write code from scratch and so on. Make sense? Anyway, I spent good decent amount of time today talking about research in computer architecture because, you know, I want your mind while you are attending this course to think about beyond the course. It's not just like, you know, here's numbers, you know, here's homework, we are done, yay, we finished, you know? Make sense? Last thing, the top places to collect information about computer architecture from them, its community is called ESKA. Have you guys heard about it? ESKA Conference 2022. It's International Symposium on Computer Architecture. This is more into software architecture, and there is, and you know, you can look into their proceedings, and you will know what is the new thing happening every year. There, you know, there is another one which is called Micro, which is more into what the hardware architecture. International Symposium on the Microarchitecture. Those are the top thing in the computer architecture. Normally, PhD students over all United States and the rest of the world submit almost like maybe 100,000 maybe papers, and those guys accept 2% per year to be published. So basically, you know, when you open their proceedings, you are looking into the top of the year. Make sense? Now we're gonna go back to our lovely course, which is the performance evaluations based on the information we have from the last time. For those people didn't accept the invitation for the GitHub, please go ahead and do it as soon as possible. What is exactly needed from me? I'm gonna send some ideas for per group, and it will be posted in an announcement. You guys look into it And if you have anything else in your mind, have been in your mind, because you know the discussion we have now about computer architecture, you would like to work as a group into it, feel free to tell me about it, and that will be awesome. Sounds good? Hello?
Sounds good, Professor.
Okay, so now what is the plan? I will give you guys by tomorrow or tonight the titles of ideas per group, and I will post an announcement. You have 1 week. You think as a group, and then on coming Monday, I will allow every single group for 3 minutes presentation to present what idea you're gonna stick with it until the rest of the semester. Okay, and I will allow you to present it like in 2-3 slides. One of the slides is gonna be what? Gantt chart. Okay.
What was that, Professor? What
I will
chart?
write it. I will write it.
Okay.
I don't want to confuse anybody here. So. Here. Regarding projects. 1, that's my homework, right? And add to the announcement, right? Possible projects for each group. This is for Mohammed, okay? For you guys too, right? You have 1 week, right? As a group to create 3 to 4 slides, including a Gantt chart for the project you will work on it for the rest of the semester. Sounds good? This is for you guys. This is for me. Any question regarding this part? Hello?
Sounds good, Professor.
Sounds good,
Yep,
Professor.
sounds good.
Yeah, sounds good.
Okay. Now, the traditional material. So 43 spring. We already finished this part, right? So we need the we already discussed all of this, right? And we stopped here. Before I move forward, any question regarding the material that I shared with you so far?
No, Professor. Seems pretty straightforward.
So much. Okay, now this is just information that you guys should be aware of it, right? Which is the historical of the processor performance over all the years since we started in 1978 up to 2014. And you could consider that since 2014 up to now, the movement went like that. It's a little bit sliding up. So in the 1978, based on to the performance, here the performance was really quite small because end of the day, the technology we had, it was not that really strong to allocate number of transistors on the chip. Then, since 1978 to 1996, the increases of the performance went up to 25% per year from every single previous year. Then there is a big jump happening from 1996 to 2003, which is considered that, 52% of every single processor that we build from the year before will be increased in terms of performance from the year before to the year after. And because of the era of jumping from 180 nanometer technology up to 7 nanometer technology and 15 nanometer technology, the jump came here to be 22% less. So why? Because we actually lose the idea of decreasing the size of transistor. Why? Because when you decrease the size of transistor, number of possible electrons between source and drain will be less. And definitely one day, there will not be any electrons between source and drain. Then the whole entire idea of building transistors on the chip will be collapsing. That's why they are looking for other solutions like silicon carbides, or even using photons or particles in the quantum instead of using semiconductors. And of course, here's a bunch of name of processors written into this study and showing you what is the maximum frequency and all of this information. And definitely, this performance number of about 52 or 22 or 25 came from the intensive study of CPI, execution time, elapsed time, average of the CPI based on the classes of the instructions we have in the processors, as we discussed before. So this is basically a kind of, you can apply these things here based on the number of the maximum frequency, and you can figure out, this increases over all the years. There is era coming because the chip have been hosting more transistors, right? And instead of having single processor with multi-core, like when I show it to you, i7, it has 6 cores, right? You can have multi-processors. But these multiprocessors, it's cool to have it on the chip, but you are making more difficult for people who build drivers, and for these people also building compilers, and the people also who is designing applications. Because end of the day, that if you don't fully use these processors in a good way, what will happen? The total performance will be dropped. Does it make sense?
Makes sense.
Super. So you can come and say that, what is the problems we can face with multiprocessors? Easy, right? One, we have to have the balancing. Are we gonna, let's say that I have a huge pile of data. Is it balanced? Every single processor will take his portion equally like the neighbor? The second, if I do this, right, if the total performance will be great, and how it will be great, right? How I'm gonna allow communication between one to the others to pass the data, especially if there is a program that has dependencies. What does it mean, dependencies? Like, I have an algorithm, and this algorithm say that, A is equal B plus C. Then, D is equal E plus F. So far, B and C, they don't have any relation with E and F. Do you guys agree? So that means, one processor can have B plus C and bring A. Other processor can have E plus F and it can go D, right? So those are parallel. But the moment that, there is, for instance, G is equal D plus A, there is no way for me to make this D plus A between these two processors. No, it will be just one processor taking those two in the consideration to bring G. So G in this case has to wait for D and A to be calculated. So in that case, there is no way for you to to process without having this result to be exist, right? So that's actually one of the programmability issues that the compiler has to take care of. Make sense? It can be even more difficult. It can be like, multi-stages, allowing that, for instance, I have Z is equal E plus G. Then, you have to wait, or, D plus G again. Then, you have to wait for a couple of cycles until this will be done. Then, all of these values will be storing in memory. Then you will move forward. So in that case, it's no longer parallelism. There is some sequential behavior will happening. So the balancing the process between of the processor will be what? Not equal anymore. One of the things that, computer architect people love to work with it is called benchmarks. So what is benchmark? They look into real problems and they make software for it and they run it on the platforms and they try to check the performance of these executions on this platform to figure out whether, these platforms are really worth to use or not. Okay, so one of the possible conclusion, maybe, we can hear in the news and say, oh, you know what? We figure out the new AI modeling that have been created based on the, for instance, recursive learning or whatever that, IBM machines are no longer really valid to be used because the performance would be dropped by this amount of percentage. So people go use AMD or use Intel. Like, you guys buying computers these days or not? I don't know. If you remember, before the pandemic, everybody was just buying Intel processors, right? Now I notice everything is AMD. Have you guys noticed that?
Yeah.
Why?
Well, Intel kind of fell behind. Not only are they pricey, but they got stuck on the 14 nanometer process for forever.
This is
Definitely.
very good. That's Christopher, it seems that you are really following the news, but there is something else, right? The people who work in benchmarking, right? Maybe they came and found out that, AMD benchmarking in terms of performance way better than Intel, right? And in that case, somebody working AI, he will come and say, oh, based on the benchmarks running on this, whatever. Oh, AMD current technology, because Christopher said 14 nanometer, right? Oh, so in that case, why I will spend my money in Intel, go buy AMD. Historically, AMD had a big problem. You guys know that? What was the problem with AMD?
Well, AMD still has some problems. For example, they don't work with all RAM types.
Correct.
So because they're a little harder to get working and they don't work with all RAM types, they're not as functionally useful in a lot of projects. However, because you can get a lot more bang for your buck, so to speak, they're more powerful processors, generally for cheaper for what you get. That's why, but like they had a lot of manufacturing processes that were bad early on.
I agree. And also I agree with one of you guys wrote in the chat, Christopher. So which is basically what heating. So Intel, their secret to stay the top on this business, the heatsink. So they build a very smart heatsink in the top of these processors, will allow you to remove the power consumed as a heat really fast, because there is something that's called dynamic frequency manager on the chips. Do you guys know that? So what is this? I will tell you. So imagine this is my processor, right? So this processor is like running in a high frequency, right? Let's say gigahertz, right? Then the chip is heating up, right? So what is the best way for you to lower the heat? Because the heat can damage the chip, right? They put, do you guys, that, right? You put the heat sink and you put the fan in the top and they call this cooling, air cooling, right? Nowadays, they already have from Zurich, which is basically what we have here in Micro Center, you can see it, right? They put like a liquid, right? Have you seen this liquid thing? And
It's like a liquid metal that helps.
Anyway, they pump liquid around the heatsink, which is what it's exchanging heat, right? Which is basically what we used to do with the nuclear reactor. You guys know that I used to work for nuclear reactors. So anyway, so we used to do that. So, you already have the core of the nuclear activities, and we put like a pumps of water, and then we put pipes of water going across this bars of uranium. Then you push cold water fast, that will take the heat, and you will recirculate it. Same thing they are doing with the liquid cooling for processors. Even though there is a new technology, they bring you the heat sink like this, and they make little holes inside the heat sink with pipes. Will go like a needles, right? Like you are threading, and then they will push the liquid inside in a way that will do what? Will cool it really, really, really fast. But while it's cooling it down, the chip also will act to help you to cool it down. What the chip will do? There is a manager that will look into the speed and decrease the speed. So it will decrease the maximum frequency. So that means it will slow your process, right? That will help the heat sink to what? Lower what? The heat. Then you will find the computer fast again, and you will find the computer slow again. That was a big problem for AMD. And Intel succeeded with this problem for a long time, until AMD figured out a solution. One thing I need to mention, which is out of this subject, but it's cool to know. IBM 2 years ago, they said, instead of cooling with heat transfer through through the liquid, right? What about if we can actually use something that's called electroblood? Have you guys heard about it? I can't tell you what is electroblood. In our body, right? Do you guys know that your brain and your liver is very hot? Temperature of your liver and your brain is like big number. Guess what is it cooling it down?
Your blood. Our blood.
Your blood, exactly. Your blood is actually transferring food and enough knowledge through the blood, while it's actually running with a pump, which is your heart, to cool it down. So why we don't do the same thing with computer instead of using wires? That's basically what was a project from the IBM Zurich. So they came and they said, we're going to make the blood, a kind of liquid like a blood that will transfer charge between components on the computers, and still we are pumping it like heart that will cool it down. Can you imagine that? This project started 2017. IBM already published around 1,000 US patent out of this. And by the way, IBM is one of the top company in the whole entire world for producing patents per year. You guys know that? I already have a couple of US patents with them and the Department of Defense. So some of those ideas really graded in use in a security clearance project. But in general, it's a part of the performance evaluation. Okay. Anyway, back to the benchmarks. So in the benchmarks, we look into the execution time, elapsed time, CPI times, and that will be for set of problems. Like for instance, guess what is the most famous benchmark you can ever have? Image processing based benchmarks, like edge detection, image filtering, image corrosion, and looking into the intensity in the images and so on, and even videos. There are some set of benchmarks that are small and tiny. Example, let's say that Christopher Watson, he came and said that I'm gonna build a full loop, and this full loop will be allowing me to write in every single stage in the memory. So you will be writing anything in the memory, and then you will read it back. And the idea of this is to look into the response time of the memory. This is called a small benchmark, but it can be misused because you can run it in a different compiler in a different computer and say, oh look, this computer is slow, without taking into consideration actually the compiler of this program is different than the one in your other platform. So that's why small benchmark easier for architects and designers to evaluate fast. Easy to standardize the larger program like image processing and video processing, but it can be abused and misused. Make sense? What are the most famous benchmarks you have? I know it's 2:15, so give me 1 minute and we'll be done, okay? So there is, the era was CPU, right? Like PCs we are using. So there is a very famous benchmark, it's called spec. And this spec is bunch of measurement of program like image processing I told you, and it changed from time to time, right? They look into the execution time, elapsed time, which is involving the IO and memory responding, and web browsing. The new one is 2017, and there is 2006, and I already left you a couple of the links in case you would like to look into it. There is another platform people look into it, right? With GPU. You guys know GPU, right? In GPU, the architecture is different than CPU. There is thousands of processing elements with high bandwidth memory. And there is a professor, his name is Kevin Scudder from University of Virginia. I used to work with him. We built something that's called Rodinia. So Rodinia is benchmarking for the GPU talking to CPU. And this paper got cited like a couple of 3,000 citations. So normally, they already have a ton of image processing application optimized in memory, optimized in CPU, optimized in GPU. They run it with the CPU and GPU together, and they look into the performance of both of them. And they call this heterogeneous system. So if you are looking into the platform by itself, CPU or GPU or FPGA, if you put them together and they are running for a specific mission, they call it what? Heterogeneous system. We're gonna stop here and we're gonna continue the part which is talking about, where exactly in the system we can blame, and from there we can upgrade, so we can look into how much speed up we'll gain. That will be by next time. Do you guys have any questions so far?
No questions.
Everything's clear, or is there anything confusing you?
I think it's clear for now.
Okay, so please, if something is not clear, something is raising concern to you, or something need to be redo it or something, stop me. We can talk and we can clear it up, because the story of computer architecture is very interesting. And there is a bunch of jobs for the computer architecture across the country. And by the way, they pay very well. They pay up to like maybe 200K and 300K for this job. ARM, for instance, you guys know ARM company, right? ARM is looking for people to evaluating DRAMs for almost like 300K. And they're fresh graduate. Okay. Hello. So thanks so much, guys. It was my pleasure to talk to you. Please don't forget to accept the invitation for the GitHub, and the video recorded version of this lecture will be loaded into week 3 under modules. And then, there is announcement will be sent to you tonight or tomorrow morning about every single group possible project, and we'll move forward. Okay.
Sounds
Yeah,
Hello.
good,
sounds good.
Professor.
Yes, thank you.
Thanks
Thank
so much. And I'm looking forward to see you on campus soon. Okay. Thank you.
Likewise.
Have a nice
Professor.
day.
Take care.
Thank you. Bye-bye.
Take care.
Goodbye.
Professor,
Yes.
I just have a quick question.